begin today with an acknowledgement of country. So I'd like to say that in the spirit of reconciliation, Cengage Australia acknowledges the traditional custodians of the country throughout Australia and their connections to land, sea and community. We pay our respect to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander peoples today. Now I'd like to introduce your presenter. Dirk Strasser is a very experienced teacher and former head of mathematics and a lead author and senior publisher of mathematics series for over 30 years. He has published and co-written 8 best-selling mathematics series for Heinemann and Pearson and won several education publishing awards. He's, as I said, a former teacher, and he is also the co-publisher and co-author of our new series for VICmaths. Over to you, Dirk.
All right, thanks, Jess. Welcome, everyone. Great to see we've got some pretty good numbers for this. I hope you get a lot out of this Mastering Matrices webinar. We've got a wide range of experience here. We've got sort of people who haven't taught matrices at all before. We've got and then we've got others at the other end of the scale who have been teaching the matrices module in further for years, and really what they're here for is to find out about the new topics, which is Leslie matrices. So what I've done is I'm going to start very basic. As you can tell by my first slide, it's about as basic as you can get with matrices, and I'm going to spend half of the time covering the basics of the course as it currently is, and it's been for a number of years, and the other half I'll be spending a fair bit of time about Leslie matrices. So both sides will get reasonably good coverage, even though there's quite a bit to get covered with this. So I'll move ahead with this. So we've got matrices, as it says there, rectangular arrangement of numbers organized in rows and columns, shown in square brackets. So there we have a matrix with 4 rows and 2 columns. Believe it or not, some students do have problems identifying which is a row and which is a column. So that's, you know, sort of a starting point, I think, with everything. This is a 4x2 matrix. The order of it is 4x2. We always say the number of rows first before the number of columns. So by the way, everything I'm showing here is coming from the VICmaths textbook. So you can sort of see, I hope that the clarity and the succinctness of the way that we try to present the theory. Of course, this is different to what's in the textbook because it's I've cut pieces out and I've moved them around and whatever. But just to give you an idea, so here we go. It's the numbers in the matrix are called elements, and that particular one that I've got circled there is A32. Well, A32. So it's the third row, second column, the element in the third row and the second column, and you can see that we use lowercase a for the elements to locate the elements, for example, and capital A for matrices. So the notation is important, obviously. I just want to, this is the very first worked example that we cover, that we do. And I just want to say that with worked examples and with the structure of the whole book, what we've tried to do is to try to look at, well, what is it that the exams actually require students to do? And we've worked backwards, right all the way back to the worked examples and the theory. So this worked example was deliberately done to actually with a particular problem that students have, or a particular type of question in mind. So it's a fairly easy one to start off with, but if you can see from this, there's a school production, 4 different types of tickets, 3 ways of selling them, and the question asks, what is the what's the matrix that could be used to show the number of adult tickets sold at the theatre and state its order? Now, finding the adult tickets sold at the theatre, that's relatively easy because that's just a identifying it from the table. But the correct answer is this, but it's not that. And there have been examiners' reports that say that on exams, students even got a simple question like this incorrect because they didn't put the square brackets around a single number. So obviously, you can't just write a number. It's got to have square brackets around it, even if it's just a single number. The second part of the question should state its order. Well, the order is clearly is 1 by 1. It's got 1 row and 1 column. But even if those of you are familiar with last year's Further Maths Exam 1, one of the questions was similar to this, where you were just asked for an order. And in the examiner's report, the examiner said there were an awful lot of incorrect answers. So, for example, that's incorrect. Putting brackets around it is incorrect. I mean, it's one by one. I mean, it looks like a multiplication sign, but it really means 1 by 1. Square brackets is also incorrect. Sort of coordinates, no. Even writing 1 by 1, which is getting pretty tough because you actually say it as 1 by 1, but and 1 row, 1 column. All of those were incorrect. Now, we make a lot of use of success percentages, which are based on the data that's given in those examination reports. So, for example, that question where students last year were just asked for the simple order of a matrix, and they got, 93% got it right, which you would hope it was like, I think the first question, and it should be simple, but 7%, even 7% getting it wrong is just, is still a lot of people. So even at this basic level, there's things that we want to make sure that students actually get right from the beginning. You can see here that a lot of matrices, the topic matrices, if you're teaching it for the first time, is about, there's definitions, especially at the start. And some of them are simple or obvious. I suppose a row matrix is fairly obvious that it's going to be a matrix consisting of a single row. Column matrix, similar. Square matrix is obviously in the shape of a square. I mean, you can see I've got the same number of rows as columns. A zero matrix has zeros. By the way, as you can see, a lot of the theory that we present has this table approach where we're trying to sort of get all the information together. Like, you've got a description of it, you've got an example, you've got the order of it, rather than just sort of listing text, a whole heap of text. We've tried to sort of break it up as much as possible. Those 4 are probably fairly easy. Summing matrix, it's probably not obvious from the name that there are, it's a row or column matrix where the elements are 1. Binary, yep, either a 0 or 1. Permutation, probably not obvious from the name what that is, but it's where every row and column has exactly one number 1 in it. So the zeros everywhere else. By the way, those green ones that I just showed were for general 12 only. I'm actually using that symbol there, that general 12 only, to use it to get across the fact that Year 11 general and Year 12 general in matrices has a lot of overlap, like a huge amount of overlap. I mean, we obviously repeat the content in Year 12, but with different, questions and examples and all that sort of thing. But it is essentially the same content. So I'm just going to be saying, if I don't say it's general 12 only or make some other specific comment, it's going to be applicable to both Year 11 and to 12 general. So those green ones there that I've circled are Year 12. Another list of definitions, I guess, of matrices, which are important. I mean, they're sort of the basis of what you work with. They're to do with diagonals, and you really need to know your diagonals for this, and also they're all square matrices. Now, looking at this, the definition of a leading diagonal is this diagonal that goes from the top left to the bottom right. That's important for these definitions. And also, there's a sub-diagonal, which is the diagonal immediately below the leading diagonal. That's actually new because it's part of a Leslie matrix definition. So we've included it early on with the definition, so it doesn't surprise students down the track. but obviously that is general 12 only, anything to do with Leslie matrix. So anyway, these are the definitions. We have a symmetric matrix, which I think is the hardest to visualize in some ways. I'm hoping you can see that the sixes, we've tried to use colors there to show the symmetry. The 6 there is sort of, if you look at the leading diagonal, is sort of the line of symmetry there. They are symmetric. The -8's are symmetric, and the 2's. So that's probably the hardest one there to get to sort of grasp. Diagonals matrix, fairly straightforward. It's where there's a where all the elements except the ones in the leading diagonal are 0. Identity matrix is where the it's a diagonal matrix where all the elements are 1. Upper triangular has all 0s below the leading diagonal, and lower triangle has all 0s above the leading diagonal. And again, those green ones are general 12 only. So really the identity matrix out of all of those is the only thing that appears in year 11. I'm not going to spend a lot of time operations with matrices because students tend to find this relatively easy. The concept of equal matrices is pretty important though. If you've got 2 matrices like that example there, then if they're equal, C has to be equal to 2, because the definition of equality for matrices is that every element is the same. So for example, it doesn't matter that there's all 3s in all of them. If there's different number of 3s and there was a different order, they're not equal. Every element has to be the same for 2 matrices to be equal. We'll have a look at addition of matrices, which is fairly straightforward. It involves adding the matching elements in each of the 2 matrices to get the answer of the matrix, the answer matrix. So, for example, you would do the first matrix of each one gives added together gives the first matrix of the answer. You can see that there's A is a 2 by 2 matrix, so is B, and the answer is also a 2 by 2. So only matrices that have exactly the same order can be added or subtracted, and the answer we get has the same order as the original 2 matrices. So it's fairly limited in what can actually be added and subtracted in terms of matrices. There's a lot of matrices that can't be. Scalar multiplication is the other thing I just want to quickly mention. Scalar, which is one of those terms that sort of throws students sometimes, is just the term that we use for a number when it's not inside a matrix, when we're using matrices, just to distinguish. So really, if you're multiplying a matrix by a number, then you multiply each term, each element in that matrix by that number. And you can see that they're all 3 by 2s. So with scalar multiplication can be done with any matrix. And the answer you would get is the same order as the original matrix. Multiplying matrices looks messy, and it is quite tedious, but it involves multiplying the elements of each row in the first matrix by the elements of each column in the second matrix and adding them, for example. I hope that visual sort of makes it clear. That's giving every step of that matrix multiplication. You can see how the matrices are multiplied together there. What happens is that you get a, I mean, A is a 2 by 3 matrix, B is a 3 by 2, and C is 2 by 2. So obviously something is happening there. For those of you who aren't familiar with matrices, something's happening there in terms of where, you know, what's happening with the orders, I guess, is something that needs to be teased out. So this is important. And if we think about it in terms of 2 matrices being multiplied together, an m by n by and n by q, then you can do the matrix. In other words, the matrix's product is defined if those 2 orders are the same. Okay, so both 5 or 3 or 2 or whatever, they've got to be the same, or else you can't multiply. And also, if you look at the answer C, the first, the order of the row of the first matrix becomes the order of the answer, and the order of the second column, the column of the second matrix becomes the order of the column in the answer. So that diagram sort of summarizes what happens between the matrices when they're multiplied together. Goes without saying, order is important when multiplying matrices. In fact, most of the times the AB doesn't equal BA, and in fact, even if AB exists, BA doesn't exist. So it's pretty crucial where you multiply the matrix, whether it's on the left or whether it's on the right. Of course, most matrix calculations, particularly once you get past 2 by 2 matrices, are done by using CAS. So we've done a very succinct way of looking at using CAS, because it's important. I mean, students need to be able to do this. They're not going to be able to answer the questions in the exam unless they're really efficient in their use of their CAS. So we have, if you get a chance when you're looking at the page, please have a close look at how we've done using CAS, because we've done a really an easy to use way of presenting this, which is a bit different to what has been around. Okay, I'm just going to briefly talk about the identity matrix. You may wonder, well, what's so important about it? If you remember, it's the matrix, the square matrix, where there's all ones in the leading diagonal and zeros everywhere else. So it's like these. Basically, it acts like a 1 when multiplying regular numbers. So it's like the number 1 for matrices. So when you multiply a matrix by an identity matrix, the matrix is unchanged. Those of you not familiar with matrices may then say, well, okay, big deal. But you know, I mean, the number 1 is very important in our number system, and therefore also the identity matrix ends up being pretty important when it comes to matrices as well. Mainly because it's involved in the inverse matrix. The definition of the inverse matrix is given here. It's the matrix when multiplied by A. When you multiply by A, it results in the identity matrix. So it acts like the inverse of a regular number. So it's really the equivalent of saying 5 and a 5th inverses of each other, because when you multiply them together, you get 1. So this is, yeah, that's the way to think of it, I think. There's an example of 2 matrices that are inverses of each other. You can see that through the calculation there, they end up as the identity matrix at the end. So when it comes to inverse matrices, only square matrices have inverses, but slightly confusingly, not all square matrices have inverses. So there's a very small number, it's a certain number of square matrices have inverses. So it really doesn't apply to all matrices. To find an inverse of a matrix, we first need to find the determinant. That gives you the formula for it. I'm not going to go through it now. It looks a little bit messy there, but it's you know, usually students can cope with that pretty well after they've done a couple of examples. The important thing is that the inverse does not exist when the determinant is 0. So that's a calculation that you do, sorry, from the numbers in the matrix. And if that's 0, the inverse doesn't exist. Again, using CAS is most important here, because you would generally find an inverse using CAS, not trying to do it with that formula. Although students do need to know how to use all of that, because the way that the examiners ask the questions some of them do require students to be able to know exactly what it is you're multiplying and not multiplying and so on to get an inverse. Solving simultaneous equations using matrices is the big change that's been taken out of the Year 12 course. So that's no longer in here. In fact, this is what they've done is they've taken out this and replaced it with Leslie matrices, basically. However, it is in the Year 11 course. So it's sort of a slightly unusual, something's dropped down to make room for Leslie matrices. Once you get onto applications, that's when sort of things become interesting with matrices. Communication matrices are a really important sort of application of matrices. Now, communication links can be shown either by a diagram or a matrix. Now, it's often good to show a communication diagram first, because you can see from here who can communicate with whom. You can see from that A can communicate with D, and D can communicate with A. A can't communicate at all with B, and so on. So the arrows indicate communication. And communication matrices are square binary matrices that show direct links with ones. So if there is a communication, it's shown by a 1. If there's no communication, it's shown by a 0. So the equivalent communication matrix for that communication diagram has it looks like that. And you can see from that hopefully by the colors, the A to D, A can communicate with D is shown here with the with a communication diagram with an arrow. Over on the matrix, we can see that there's a sender there and there's a receiver is the column. So if you want to have A sending to D is this one here. So it's shown with a 1. So we know that A can communicate with D. And here too, you've got on the communication diagram, you've got D communicates with C. And here it's shown in the matrix the 1 by D communicating with C there. So communication matrix shows the same thing as that diagram. But once you've got it in matrix form, you can actually manipulate it and do all sorts of things with it, which you can't do when it's in diagram form. Communication with yourself isn't considered communication. So basically, this here says A communicates with A. Well, they're always zeros. They're just given a 0 because it's not considered true communication in the sense that we're looking at it here. So the leading diagonal in these communication matrices always consists of just zeros, which is the point I was making there. Although, let's have a look at this. A cannot communicate with D according to the diagram. With C. A cannot communicate with C according to the diagram, and it can't either according to the matrix, obviously. But it can communicate in a two-step communication. So in the diagram, you can see A can communicate with D with a green arrow, and D then can communicate with C. So that's how A could communicate with C via another person. And similarly, here A could communicate with D, and D could communicate with C, so you could get a message to C that way. So that's called a two-step communication, which after all is a communication as well, because the message can get there in the end. Now this is where it sort of gets interesting in terms of what you can do with a communication matrix. If you square, in other words, multiply it by itself, a communication matrix, it gives you the number of two-step communications. So looking at this table, for example, we've got M in the first column, but let's just focus on the second column, M squared. We've got the square, when you square M, you get this matrix here in this column, and you can see there's a 1 from A to C, which says that there is one two-step way that A can communicate with C, so via another person. It gives you the two-step communication just by squaring the matrix. If you add M and M squared together, you get all the 1- and 2-step communications. So it's all those ways that can be done. You've got to ignore the leading diagonal in these though, because they're still about, I mean, it's meaningless, for example, with M squared here to say, well, A can communicate with itself via someone else one way, it's true, but it doesn't really help any practical problem. Okay, so basically, although m squared gives the number of two-step communications, you would need to look back on m to see exactly what those two-step communications are. So you can't tell from that matrix that what the two-step communication is between A and C. So you'd have to go from, you can see that A to D and then D to C that way from just the original matrix. Dominance matrices involve situations where there's clear winners and losers. For example, a round robin tournament. There has to be a winner and a loser in a dominance. You can't have draws and things like that. So it's similar to communication, except all the arrows in a dominance diagram are one way. So here's an example of a dominance diagram. Clear, so you can see that A dominates B. You couldn't, I mean, it would make no sense to say that B dominates A as well, because it's just nonsensical. So you've got the arrows only going one way. The dominance matrix is essentially the same as a communication matrix. Because there are less arrows in the diagram and therefore less communication or less connections, there are fewer ones in the dominance matrix, but that's by looking at it, that is the main difference. These would often be labeled winners, losers. You can, and also you can see here that means A dominates D, and you can see here that that means D dominates C. Summing each row in a dominance matrix gives you the one-step dominance scores, or in other words, how many wins each participant has. So adding up those, you can see that the scores are A has won twice and C has also won twice. So that means you can tell from that. The other thing that happens now, I'm not going to, I won't cover it, but the same thing happens here as with communication matrices. Excuse me. You can have if you square it, you end up with the two-step dominances, and therefore you can find out who had more two-step dominances, and therefore was the ultimate winner. Transition matrices sorry about that. Transition matrices are square matrices that show a change from one state to another, where the change follows the same rule each time. The important thing with transition matrices is that the total number involved in the transition stays the same, and that's often lost on students. So nothing gets added, it just gets moved or taken away, it just gets moved around. This example here involves two shopping centres, Eastworld and Highton, and how shoppers change the centre they visit from one week to the next. So you can see here that with this 75% attached to E, to Eastworld, 75% of shoppers who go to Eastworld 1 week will go to Eastworld the next week. And over here, 10% of shoppers who shop at Highton 1 week will shop at Eastworld the next week. The matching transition diagram is this. Excuse me. You can see that they use decimals. We use decimals instead of percentages in the transition diagram, but it works the same way, so that here, this week, you can see the column there is this week, and this over here is next week. This week, Eastworld, next week, Eastworld, next week, Eastworld, 0.75 will be in Eastworld next week, is the equivalent of the the 75% over here, and the same thing with the 0.1. Excuse me. I had a feeling this would happen. Okay. For some reason it's stuck. Okay. The important thing about transition matrices is that the columns add to 1. This is part of that idea of things not changing. The total numbers don't change. That's one of the reasons why this is happening here. So this is a feature of transition matrices, that the columns need to add to 1, and that's important for a number of questions that get asked. The power of transition matrices is that they can be used to make predictions, and they're done via a recurrence relation, and it's essentially the same as the recurrence relation that appear in financial maths. So you'd be familiar with them. It's just with matrices, but the principle is exactly the same, where you start with an initial state matrix and you just use a recurrence relation to get the next one, and then you get that value and you continue and so on. So for example, here, this worked example, they're asking for a matrix recurrence relation, and we've got the shopper scenario here where there's 23,000 going to East World and 12,000 going to Highton. The initial state matrix is this, based on those two figures, using the recurrence relation and the transition matrix, you get that. So therefore, now that you want to predict what happens next week, that means you want to find S1, substitute in and do the multiplication with CAS, and you get those two values. So therefore, you know how many shoppers go to East World and how many go to Highton the next week. There's also a rule, the state matrix rule. If you think back to financial maths, where you've got the recurrence relations there and rules, so you've got both, and you're sometimes asked to use one or the other. So the same thing here. So in this case, you want to ask how many trucks are at each depot after 8 days. Sorry, after 6 days. It's just a matter of raising the transition matrix to the power using CAS and doing the just getting the answer, pulling that out from the answer there, so you can see from that the number of trucks that have that are there that are at each depot after 6 days. What's really interesting with transition matrices is that a regular transition matrix raised to a high power, what usually happens is the elements stop changing. So for example, for that transition matrix, if you raise it to the power of, say, 39 and then to the power of 40, you actually end up with the same answer. So it's actually stabilized. It's despite all the stuff moving around all the time, the transition matrix ends up being the same in the long term. And that's always a key word to look for in questions, the word long term. So what really happens is that the state matrix gets to a point where it stops changing from one transition to the next, and that's called the equilibrium state matrix. Just if you want to see how that calculates for here, we've got with an initial state matrix here of included in the calculation, and end up getting the same answer in the end. So we've got an equilibrium state matrix at the end there, where it's no matter how many times you keep going now, it's going to stay at that value. Okay, Leslie matrices. I think it's hard to. I needed to cover transition matrix reasonably well, because it's pretty hard to follow what Leslie matrices are about without knowing what transition matrices are. It follows on logically. They're similar in some ways. Leslie matrices model how animal populations change by taking into account how birth rates and survival rates change depending on the animal's age. So there's sort of transitions as well happening here, but with transition matrices, there are sometimes questions where you've got, I don't know, a type of bird, a group of birds moving from one nesting place to another, but basically they don't take into account births and deaths in that. This is much more realistic. It actually takes into account a lot of information about those particular animals. Since only females giving birth, Leslie matrices count only the females in the population. So that's one thing to keep in mind, because it does affect a number of questions. Because if you're talking about a total population, you're going to have to, like double the figure that you're getting, because all you're getting is just the female numbers in the figures always. Leslie matrices are created from tables of information that contain female birth and survival rates of different age groups. Without those tables, you can't do it. You need that information. And the first step to set up a table is to decide on suitable age groups, and these depend on the animal's lifespan. So here are some examples. The golden hamster has a lifespan of 4 years. So it's, the table that you would draw up for this in preparation for Leslie matrix would probably, the most logical one would be to do it into year groups, so that you'd have you would count all the number of golden hamsters for example, between 0 and 1, and then in the second group you've got all the 1-year-olds, and then you've got the 2-year-olds, you've got the 3-year-olds. No one lives past, the lifespan is 4, so they're not going to live past 4. Labord's chameleon, and these are all actual figures, has a lifespan of 6 months, so you would probably do it by month, so that you will end up with 6 categories there. A cockatoo lives 50 years. I think splitting it up into sort of 10-year groups would probably be the way to do that, because it's it's probably not manageable doing it any other way. So that's the starting point. You need these age groups. You can't do anything until you've got those age groups. The following shows the table and corresponding Leslie matrix for a colony of lizards. So this is an example. This is the female birth and survival rate table for the lizards. Okay, so you've got a birth rate attached to each group and a survival rate. I'll show you the corresponding Leslie matrix that shows that information. Now, as you can see, hopefully with the way that the colours used there, the first row of the Leslie matrix is just the birth rates, and the survival rates appear as the sub-diagonal in the Leslie matrix, which is why I mentioned sub-diagonal definition earlier. But you'll notice that the 0 in the last one doesn't appear in the matrix, because it's irrelevant, because they don't survive beyond 4 years if you know what their life, we're assuming we know what their lifespan is. So that's how a Leslie matrix looks. Just to sort of be clear on this. So what both the table and the Leslie matrix are saying is that on average, female lizards aged 0 to 1, so they're not yet 1 year old, give birth to 0.2 female lizards in a year and have either 0.3 or 30% chance of surviving to be 1 year old, to go to the next group, age group. Similarly, the next age group, for the average female lizards age 1, so it's 1 year olds, give birth to 0.6 female lizards. So we're only talking about the female lizards they're giving birth to, and not total, and have a 0.8 or 80% chance of surviving to be 2, and so on. So it's that's sort of the information that you get from both the table and for the Leslie matrix. Now, birth rates can be numbers greater than 1. Obviously, you can give birth to, or certain animals can give birth to large numbers, or in a time span, but survival rates can't be greater than 1. So the blue ones there can't be greater than 1 because you can't survive, more than 100% can't survive to be the next age group. So just to summarize it, Leslie matrices are square matrices which calculate female populations where birth rates are given for each age group in the first row, survival rates are given as decimals for each group in the subdiagonal, and zeros everywhere else. And then there's an explanation about what that means, which I've already been through. I'm going to show you a question. Now, we have 3 sections in each of our exercises in VICmaths. We have a recap, which covers the previous exercise, just as a sort of a warm-up and a sort of a cumulative approach to questions. There's sort of 2 questions at the start. There is the mastery questions, which I'll speak about again in a moment, and there's exam practice in each exercise. Exam practice has VCAR questions where they're available, the ones that are the most suitable, and they're graded according to the success percentages. But Leslie matrices, we don't have any VCAR questions, but what we've done is we've had a close look at how the VCAR questions have been structured for transition matrices in particular, but also just the general pattern, and come up with the type of structure for exam style questions that would occur. So this is an example of one of those. How many of the following could be Leslie matrices? This is sort of a common structure for a multiple choice question in matrices. So let's have a look at that question. How many of those could be Leslie matrices? Well, let's look at the first one. That 0.8 should probably jump out because really there should only be numbers, non-zero numbers in the first row and in the subdiagonal, and that should be 0 if that was going to be a Leslie matrix. So that's not a Leslie matrix. In the second one, yes, it looks like a Leslie matrix until you look at that, because I said that the survival rates can't be greater than 1. So we've got a number greater than 1 in that subdiagonal. So that can't be a Leslie matrix. Now that one, you might think, oh, does that look like one? It's got, I mean, it hasn't got any of the problems of the previous ones, but Leslie matrix are square matrices, and that's not a square matrix. So that isn't one for that reason. That's the only one that is. Obviously, that first row, which is the birth rate, it can be 0 for an age group, because obviously the age group could be either too young or too old to have any babies. So it can be 0, but anyway, so that's fine. And this would be the subdiagonal in that case, and it's not more than 1, so that's and it's not 0, so that works. So that in that case, the correct answer is B. 1. Now, let me talk about how mastery works in VICmaths with a Leslie matrix example. This is probably this is the first worked example in Leslie matrices, and you can see you're given some information about capybaras in the Amazon. Apparently, I think they're the largest rodent or something in the world. And it looks at their survival rates and birth rates and so on. Now, this is a worked example. So a worked example obviously has the question, and then it has steps explaining step by step what you need to do. And then the working is here in blue, what you would expect students to actually do at each step. Now, they're the worked examples in the textbook, but what we've also got as part of this sort of mastery circle is we have a matched example in our workbooks. So student book has the worked example. The matched example has it's a very similar example called a matched example, same title. In fact, the steps are identical, but it's a slightly different context, and obviously the numbers are different. So we would every worked example in the textbook has a matched example in the workbook. So students end up having a scaffolded way of doing their very first question after a worked example in this workbook. So you've still got this here. these explanations. You can go back to the worked example to look at it, and it really holds their hand as they go through that, and it encourages them to show working. I mean, there's space for working at every step here, and so many students lose marks in exam 2 in general, of what used to be further, because they don't show their working. So I think this workbook is going to really encourage students to show more working than what they currently do. But it's a match, so we've got a worked example, the matched example. Also, there are answers to these in the workbook, so they can check whether their final answer's right. But more than that, in Nelson MindTap, which is our brand new platform that is associated with VICmaths, we have the full solution. So at every step, what they should be writing. Now, students, you can, the way Nelson MindTap works is you can give access of these to your students, or not. You could use them for other things as well, I guess, because it's effectively another example with full working shown. So that you'll hear a lot more from the sales team about Nelson MindTap. And then students are ready to do the first mastery question, which is attached to that worked example. So you can see we're stepping them through from the initial worked example to a matched example to a mastery question in the exercise that's attached to that worked example. So again, it's essentially the same question with different numbers, slightly different context, and so on. So they're really led through the skills and the things that they need to know and be able to do very carefully through the way we've set up this sort of integrated process. Okay, the Leslie matrices also have a recurrence relation, which looks almost identical to the transition matrix one, and they also have a rule which looks exactly the same as well, except we're using an L instead of a T. So that works the same way. Essentially, there's nothing new about the way they work as a recurrence relation. You need to obviously be told what the initial numbers of whatever it is, whether it's Liz's or whatever, are in each age group, because that gives you your initial state matrix. And often we place the age groups here just for reference on that initial state matrix. So, but that's not any different from transition matrices. So using the recurrence relation, you would look at find S1 using the formula, using the Leslie matrix and the initial state matrix, and you get those results there. And then you'd use the answer you got for S1 to find S2, and so on. So you can see, although we started initially with, I think, 33 one-year-olds, there's now 14 after 1 year, and well, there's 38 after 2 years. So you can see them bouncing around a bit there. Again, you can use the rule the similar way we do with transition matrices. So you can find the number of female, remember this is the female lizards too you're finding, not the total population. It's always the female ones. After 12 years, so you raise the Leslie matrix to the power 12, multiply, and so on, you get, after 12 years, there's 17 one-year-old lizards there. We have these exam hacks throughout to help with sort of the tips and tricks and so on about what happens in exams. Basically, this one says, assume that half the population is female and half is male, unless you're told otherwise. That's really all you can do, but you've got to watch questions that ask for total populations, for example, because I've got a feeling that's one of the tricks that they're going to be putting in to catch out students who forget that this is just talking about females. Long term, like the way we look at we looked at long term, what happens long term for transition matrices. We're also looking at them in terms of what happens with Leslie matrices. If you remember, for transition matrices, it ends up, for a regular one, it ends up being coming to an equilibrium. It just it stabilizes and becomes the one. It doesn't change anymore. That doesn't happen with Leslie matrices, but in the long term, one of three things happens. Either the populations increase, they decrease, or they cycle. It's one of those three things will happen over time, but they won't stabilize like transition matrices. So a cycle here that involves a repeating pattern of state matrices that start and end with the initial state matrix. So you always start with an initial and you go through a few changes, then it comes back to that initial state matrix again, and so it just keeps doing that. Okay. This is trying to explain what how you can work out what's going to happen by looking at the matrix. Which one of those three options? So in the long term, the population model by an m by m Leslie matrix L will increase if the total population of this the mth state matrix is greater than the total population of the initial state matrix. It will decrease if the if that SM is less than the total population of the initial state matrix, or it'll cycle every m time periods if the two are equal. So the key thing is to find out what SM is. And remember, the M is the order of that matrix. It's an m by m matrix. So it's a 3 by 3 matrix, and we're looking for S3, for example. So here, this question asks, for this Leslie matrix, does it, in the long term, will it increase, decrease, or cycle? Since it's 3 by 3, we need to find, to determine that, we need to find S3. So we would use the rule for Leslie matrices. You wouldn't go to the trouble of doing the recurrence relation method. So you raise the Leslie matrix to a power 3, and you can see from that answer that S3 ends up being exactly the same as S0. So they're the same. So we compare them. Since they're the same, the population will cycle every 3 time periods. Okay, I'm going to hand over to Anne-Marie now, who's going to talk in more detail about the sort of the components and features behind Nelson VICmaths. We're going to take questions about everything right at the end. Okay, thanks.
Thank you, Dirk. You did really well there. You can have a little break from the talking for a short while. Before we go to questions, I'll just take a few minutes to introduce you to the VICmaths series and what is available to you. So VICmaths is built upon research into the science of learning, a complete learning solution addressing teacher and student pain points and helping students achieve in maths. As you will see here, we've got a range of products across the series, from general maths, maths methods, specialist maths, and foundation maths for year 11 and 12 student books. For the purpose of today, I'll just highlight a few key points regarding the student books, but I would encourage you to reach out to your learning consultants to request proofs, or we're most happy to meet with you, be it a short meeting in person or virtually, or a faculty presentation. So I guess I'd highlight that through the VICmaths series, we clearly follow the study design. It's student-friendly and approachable text with clear and concise theory. There's lots of opportunities for practice and revision embedded in each chapter, and some of those features have been introduced by Dirk through the presentation, from recap questions to the success percentages, to the mastery questions, to exam practice, exam hacks, and VCE question analysis. So these will help with students with recall, be exam ready, and saves you time in preparing questions and reducing stress all round. Dirk, if we have a look of, yeah, sorry, just move back, yeah, one more. So we'll just summarize by saying that with the student books, there are a few different options available. So you can have the student book and the digital access for $89.95. You can have digital only through the NelsonNet platform, which will be available at $49.95, or you can have a pack, which is the student book and the mastery workbook for $99.95. That represents a saving of $19.95. Just on the digital platform, so the digital platform is the online learning space where you will have access to the ebook, the interactives, and online assessment. We will have videos, including Darren Smith, the Maths Guru, helping you to engage students and monitor progress. And the Maths Mastery workbooks will be available for general maths, maths methods, and specialist maths for year 11 and 12. We won't have a mastery workbook for foundation maths. Lots of opportunity for practice and for students to show their working out. These are available at $29.95, or you can have a student book and workbook pack for $99.95. Dirk, if we could move to the next slide, lovely, thank you. So we've got the A+ VICmaths study guides, which are available for general maths and maths methods. These are comprehensive revision and exam preparation guides. They will include summary notes, 400 questions, graduated questions, different style of exam style questions, tips and answers, all for $34.95. And the last slide, Dirk. So I just finished by speaking on behalf of the Victorian team of learning consultants. We are here to support you with any queries or anything you need. We do, as I mentioned, we do have page proofs available. Simply reach out to your learning consultant, be that myself, Anne-Marie Mosley, Kim Lowe, or Gillian Lim, and we will be happy to provide them to you. We are also available to meet with you, be it a short meeting, a Zoom meeting, or in person. We know that we're living in challenging times in school communities at the moment, so we're happy to be flexible. So reach out today for your proofs and or to organise a meeting time, and I thank you very much for your time. And now we will deal with any questions. Over to you, Jess.
Thanks, guys. And thank you to everyone for sticking with us. We'll just go through some of the questions that didn't get answered earlier. So Dirk, do multiplication steps need to be shown in an examination, or can they still be performed using CAS?
Look, no, nothing's changed from that point of view. So that, yes, they can still be performed using CAS. There would only be, if it was a show that question in exam 2, then obviously, yes, you'd need to show the steps, but otherwise not, no.
Okay, and next question. If solving a system of equations is no longer being covered in General 3-4, what is the identity matrix being used for?
Yeah, that's a good question. Yes, I don't know. It's used, well, inverse is still there, so you need to have the identity matrix for inverses, but in terms of actual practical applications, no, there'll be some theoretical questions about it, but not practical, none of those no applications basically.
Okay, and just flagging if anyone else did have a last minute question, please throw it in the Q&A now. We've got one more question. Oh, someone's put one in the chat. Are practice SAC tasks included in the teacher package?
Sorry, could you repeat that?
Are practice SAC tasks included in the teacher package?
No, they're not. We did, well, to give you a bit more context on that, we've looked at that, and it always becomes an issue of, you can't, as a commercial organisation, give people a SAC. You can give them something that could start them off, but they just don't allow commercial SACs to be used. So we haven't. It was always a dilemma of what is it that we can provide sort of within the actual structure of the way that the SACs work. So no, we haven't done that.
We've had a few questions come through about publishing dates, so I'll just answer that. So they'll sort of be publishing anytime between August and September for all the general titles. Except I think, yeah, so they'll be coming out, so particularly the student books, you'll see in late August and late September. So like Anne-Marie said, there are samples and page proofs available to see now. If you're interested. We had a couple more questions. In the previous Nelson VCE series, questions used in books 1 and 2 were repeated in books 3 and 4. Is this still the case?
No, the answer is no, because that was a criticism of that current series. They're not repeated. The only exception is occasionally there are some VCAR questions that are repeated because they apply to both and because they're really, really good questions. And I think it's pretty good. It's good practice to have students being able to see a VCAR question that of that quality twice. But that's sort of the exception rather than a pattern or anything. So in general, no, they're not repeated.
Awesome. Now just checking one last call for questions before we wrap up. Thank you, everyone. I know it's getting a bit late. Awesome. Thank you, Dirk, for presenting. And thank you, everyone, for coming and joining us tonight. We will send out the slides and the recording next week. And we'll send some more information about the series just so everyone can see pub dates and other information. If you would like to see samples, please reach out to our sales team. Thank you and good night.